Like the notes will come back, but right now I don't find the need for it at the moment. All right, so an index, or the plural indice, okay, is talking about the root that we are taking. So everything we've done so far, if I write something like that, okay, and I don't put a number out front, I'm taking the square root, okay? So something like when I say 4 underneath here, that is the idea that it's basically, 2 squared. The index of 2, the root 2, cancel the power 2, leaves me just 2, right? Okay. Or we can think about it as when we did 4, we broke it down to 2 and 2. That's a group of 2 objects that can come out of the radical. Okay. So basically the logic was when this is what's not written, or sometimes when they do write it, even if they do put a 2 there, okay, we're looking for the square root. Okay, so that is a symbol for a number that I multiply by itself 2 times, and that 2 right there is telling me that 2 times to get 4. So do you guys agree that 2 multiplied by itself 2 times gives me 4, right? So what if I do something like this? I change the index out front to a 3. No longer am I looking for the square root. I'm now looking for something called the cube root. But everything we've already done is exactly the same here, except for when we do the prime factorization and we were looking for groups of 2 objects, now we'll be looking for groups of, take a guess, 3 objects. That number out there tells you how many things you're looking for when you do the prime factorization. Basically what it's saying is that we read this cube root of 8. Cube root of 8 is a symbol for a number that I multiply by itself 3 times to get 8. Does anybody know that number? It is 2 again. Okay? But the way we find that is we just come to the side, do the prime factorization. 8 goes down to 4 and 2, right? 4 goes to 2 and 2. Is that a group of 3 objects? I now have 3, 2, so now my circles, or I don't call them pairings, I'll call them groupings here. My groupings in the prime factorization are looking for groups of 3 before they can come out of the radical. So take 2 times 2 times 2, what's that give you? Gives you 8. Okay. So let's do this one. Let's go cube root. Cube root of 16. So now we're going to take our 16. We're going to break it down to 2 and 8. Or if you want to go 4 and 4, that's fine as well. And then you go down to 2 and 4. And then you go 2 and 2, right? Now I'm going to circle groups of 3 things. So there's a group of 3. So that comes out in front. And now this 2 right here doesn't have anything to partner up with, right? So it goes back underneath the radical. And the only thing we have to pay attention to here is that when it goes back underneath the radical, that we put that index there. If I don't put that index there, I'm talking about square root of 2, right? And here on the cube root of 2, okay? So here's where technology kind of fails us, okay? Basically what I can do now is I want to test your quiz, and if I wanted to test your knowledge, basically I've said everything that we've done with square roots now transfers over to cube roots, right? Do the exact same stuff, except for now we're looking for groups of 3. It's the only difference, okay? Some of you have calculators that you can type in square root of 8 and it gives you the result, 2 radical 2, in the format that we want. Well, then that would provide an issue for me to test whether you know what you're doing, right? Because you're letting your calculator do it. So now I could just say, well, give me the cube root of 16. Because guess what your calculator won't do? Your calculator won't give you cube root of 16 as 2 cube root of 2. Okay? So that would allow me to test whether you know how to really do the work we've been working on for probably now about a little over a month. However, there are still commands on your calculators that we can use to see if we are doing things correctly. Basically, we can change these into all decimals to see if we do have a simplified version. Okay, so you see this symbol right here. I'm going to use Desmos, but they're I'll bring up another calculator in a moment, see if we can see a similar button. You see that button right there? Okay, so that's your square root. So all your calculators somewhere around your square root potentially will be a image like this. Now, it might not have an N there. It might have like an X or whatever. If I click that, you see how it now puts the cursor out here in front? I can put a 3 there. I can put a 16 in there. It gives me that number there. What that means, and we've done this before, if I take that number, multiply it by itself, now 3 times, we see that generates the 16 that we're looking for. Okay, so this is a symbol for that number. Okay, well, to see if I've done this right, because we said it should be 2 cube root of 2, so I could just type this in this way and see if these decimals are the same. So that tells me that these decimals are the same, that these two formats were the same. Does that make sense? Now, if you have like a TI calculator, okay, so if you guys look back here, these red ones, a lot of you have these types of calculators, right? Maybe not red, but blue or gray or whatever. If you look at your square root button, or actually let's look at it's the first row, first column. You guys see where it has pi, and then underneath it, it's got the exponent caret. Okay, the exponent caret is this, if we hit the second key, so it's different on does anybody have this calculator up here in front? Okay, so if nobody's got that one, let me do TI 30 XS. All right, so if you look in this first column here, you see this key right there, correct? Okay, so hit the second key, and then hit that caret. Okay, so if I hit that, so I'm going to write what this does. All right, so 3. Okay. So let me retract my statement, because when you hit the second key, so you hit second, and then you hit that, it probably wrote like ANS. Did it do that? And then it had like a little asterisk there, and then your root, correct? Okay. So what this is doing is basically it's taking whatever your previous answer was and making it your index. It's making it that 3 that we want. So don't do it that way. So clear, what I want you to do is clear everything out of your calculator. Just hit the clear button. Okay? Now hit, so it's just the way they're programmed to reference previous commands. If you hit second caret, it'll reference, it's looking for a number that has not been typed in. So if it sees nothing's been typed in, it defaults back to the previous answer, okay, and uses that. So type in 3 first. Type in 3. Now hit the second key. Now the caret. Okay, and that should produce something that looks like this. It should say 3, have your asterisk there, and a root, right? So what that's generating for us is that right there. Okay, that's just the way the calculator demonstrates it. If you then put 16 underneath the radical, it should then give you that same 2.5 number that we were getting on that.
Okay, so right here the code on top of it, is that what I'm
Yes, so yours is going to be, so how do you gotta hit the shift key. Yep. Yep. And yours, so yours is defaulted with a 3. I think you go, delete that. So you can delete that, and you can change it to 5. So that's one way to do it. Where you go, see this one right there.
Everything but Kent's part.
Hit that.
You're like, dude, it's just a meme, but it's actually really good options.
Anybody else questions on how to do that calculation? That only gives you the decimal version, which is just a way for us to check whether our reduced version is equivalent to what we started with. Okay, so it's just a tool to check ourselves. Let's do a few more examples here. I bid it this morning. Oh. I went out to start my car. Actually, no, I went out put my like after school stuff in my car, and my driveway had snow on it, and I had these like sandal type shoes on, and there's no tread on the bottom of these anyways. So I go into my garage and go into my we go into my garage and it opens up into my kitchen. I stepped on our linoleum and my head was the first thing that hit the ground. Lots of bad words came out, and
You say bad words.
when I fall down, I do. Yes. Yep. Yep. Working through a couple more examples. Let's go cube root of 4,000. Okay. So what will divide 4,000? 1,004. Okay, 4 goes down to 2 and 2, right? What's 1,000 go down to? 110. 10 goes to 5 and 2. What's 100 go to? 10 and 10. And then those all go to 2 and 5, right? Okay, so I'm going to highlight my 2's. So there's 3 2's, right? So when I highlight 3 2's, that can come out. Okay. Now, can I look at these 5's? Right, I can't break them down anymore, but do they create a group of 3? So that can come out. In these 2's, do they have a group to go with? No, so they stay underneath as 2 times 2, right? So we get 10 times the cube root of 4. 10 times the cube root of 4. And now think about, a quick way to check yourself. It's the same thing happens with square roots. We talked about this. If I take this number and raise it to that power, okay? What's 10 times 10 times 10? 10 raised to the third is 1,000. Take that 1,000, multiply it by the number that's on the inside. What's 1,000 times 4? 4,000. Get you back to the beginning. Okay? So that's as far as it goes. So now instead of looking for perfect squares that are underneath the radical, we're looking for perfect cubes that are underneath the radical. Okay? And this idea, we'll only focus on like this being a 3, maybe a 4. Okay? But you can, in practice, this number could be anything that it wants to be. It could be 4, 5, 6, 7. But you approach it the exact same way every single time. So let's do. Yes, I got. Let me do one with algebra in it, and then we'll do a fraction one. So let's go cube root of 56 x to the 6th y to the 4th. Okay, so you guys take a minute and see what you come up with. Separate that. We'll separate it to 56, cube root of 56. This is exactly what we did with the square root stuff. We'll separate it this way. Okay, you guys come up with what the cube root of 56 looks like. Did you get 56 to go down to 2 times 2 times 2 times 7? So then that group of 3 2's can come out as a 2. And the 7 stays underneath the cube root. Okay? Now, we're going to play kind of a game. I'll show you at least like the long way of doing this, and then hopefully maybe that can transition into the shortcut. You guys remember if it was square root, if it was an even number, all we did was take the, like if it was x to the 10th, I'd take the square root, I'd take 10 divided by 2, and give me 5, right? So I have x to the 5th that comes out, okay? So it's a similar approach here, but I'm not just looking for even numbers now. I'm looking for things, if these exponents are multiples of 3, okay? I'm going to simply take 6, in this case, and divide it by 3. What's 6 divided by 3? 6 divided by 3? 2. So this is going to be x squared that comes out of the radical. And the reason for that is this. X to the 6 cannot be rewritten as x cubed times x cubed. That make sense? We add the exponents, right? So when I take the cube root of these, what's the cube root of x to the 3rd? Cube root and power of 3 cancel each other out. They're inverses. So it just leaves me x. Does that make sense? Cube root, power of 3, leaves me just x. Well, what's x times x? X squared. Okay? Now if I had something like x to the 9th, let's look at that one. Cube root of x to the 9th. Well, can't that be written as x to the 3rd times x to the 3rd times x to the 3rd? Take the cube root of each of those. Do the cube roots and the powers cancel out? Leaves you x times x times x, right? What's x times x times x? X to the 3rd. Is that what I get when I take 9 divided by 3? Okay, so when, I might want to write this down, when the variable power is a multiple of the index, and this is what we did when we were square root, so we're using to write it this way, is a multiple of the index, divide power by index. And that is the exponent of the variable on outside of the root symbol. That's exactly what we did. We took 6 divided by 3, and it gives us 2. We get x squared out from the radical. Now I look at y to the 4th. Y to the 4th is not a multiple of 3, right? 4 is not a multiple of 3. So what we're going to do is we're going to rewrite y to the 4th so that I do get multiples of 3 to show up. Okay? But the leftover might be a power to the first or a power to the second. Okay? Basically what we're saying here is because I'm taking the cube root, I will never have underneath the radical here with the variables, I will never have a power that is greater than 3. They're all going to be 1s and 2s when I'm fully simplified. Okay? So y to the 4th, would you guys agree y to the 4th can be rewritten as y to the 3rd times y to the 1st? Does that make sense? Can I then take the cube root of y to the 3rd and the cube root of y? What's the cube root of y to the 3rd? What happens with the root and the power? Cancel. Guys, I hope a lot of us are paying attention now and not trying to do our homework because it's not going to make sense later. Those cancel, leave me y. Now this y to the first here does not cancel with that cube root, so that stays underneath. So that's how these two, the numerical portion and the algebraic portion, simplify. So now we put them together. The 2's on the outside. X squared y is on the outside. Cube root 7's on the inside. Y to the first is on the inside. And that's our final result. It's a simplified version of that. What I'd like to do is take a moment and look at just some simpler variable components and different indices to see if we get the hang of this. If I have, let's just go the cube root of, let's say, y to the 7th right now. Okay, I want to get this y, that 7 is not a multiple of 3. So what I want to do is I want to rewrite it as y to the 6th times y to the 1st, because the 6 is a multiple of 3, right? So now if I take the cube root of y to the 6th and the cube root of y to the 1st, here we see that relationship where 6 is a multiple of 3. So now we can just do the division. What's 6 divided by 3? 2, right? So I can rewrite this then as y squared outside the radical. And now here, nothing cancels. Okay, because this, basically when this number here is less than the index, it was less than 3 in this case, there is no cancellation, there's no simplification. So it just stays the cube root of y. So what I want to show you here, how to use Desmos to make sure that we've done this right. Or your TI 83, 84, TI 30 can do it too, but you got to be a little bit more creative than what Desmos allows for. I'm just going to type in 3 and a y to the 7th. Okay, it's not going to tell me the answer, it's not going to give me anything here. But then we'll type in y squared. And then cube root of y to the 1st. Again, it's not going to give me anything. But when I say y is a number, let's just say y equals 2, does it tell me that those two decimals are the same? If those two decimals are the same, then these two formats are the same. So say it's 21. 21, 21. These two things are the same, right? So show me that these two things are the same. Okay. What if we go, let's go cube root of x to the 11th. Okay. Basically, I'm going to try to find the smallest multiple of 3. I don't know how to phrase this, but the largest multiple of 3 that is less than 11. The largest multiple of 3 that is less than 11. What is that number? What is the largest multiple of 3 that's smaller than 11? 9. So I'm going to rewrite this as x to the 9th times x to the what to get this to be 11? X squared. Good. So then I cube these, or cube root both these. What happens with this 3 and the 9? X cubed. And now these don't cancel, right? So I got then the cube root of x squared. Okay. So that being said, what if we change the index? What if we go the 7th root of x to the 16th? Now what I want to do is I want to use multiples of 7. Does that make sense? So what is the largest multiple of 7 that is less than 16? 14. So I'm going to rewrite this as x to the 14th times x squared. That will give me my 16, right? I'll now take the 7th root of that and the 7th root of that. What do I do with the 14 and the 7 here? Divide them, it gives me x squared. And then here, that doesn't happen. You can't do that. So it's just going to be 7, 7th root of x squared. Parentheses? You can. Your calculator is going to open parentheses, so you can close it. But basically, this symbol, we can keep moving it longer and longer, and it's essentially a grouping symbol itself. So they're not necessary. One of the questions was, I think, what happens with fractions, right? So say we got the cube root of 27 over 216. Okay. Same thing with all radicals, no matter what the index is, square root, cube root, 4th root, 5th root, doesn't matter. You can always break it up this way. Take the top, take the bottom, and separate them. Okay? In the next couple days, we're going to explain why that can be done. Now, if I look at my 27, let's simplify that. 3 and 9, 3 and 3, right? Is that a group of 3s? So that can come out of the radical. There's nothing left over to go underneath the radical, right? So what that tells me is that 27 is a perfect cube. 3 times 3 times 3 gives me 27. Okay. Now the 216 one. So 216, 2 and 108, 2 and 54, 2 and 27, 3 and 9, 3 and 3, right? So here's a group of 2s. And here is a group of 3s. Just want to make sure that that's correct. 2 times 2 times 2 times 3 times 3 times 3. Yep. Okay. So this group of 2s can come out, and this group of 3s can come out. There's nothing left to go underneath the radical, right? So it leaves me 3 over 6, or if I just wanted to do that and get 1/2. So that is a kind of a clever way of writing the fraction 1 over 2. Okay. There are times, and I'm not going to spend a whole lot of time with this with you guys right now, but let's say instead of that 216, let's put another 2 in there, so 432. Let's say I started with the cube root of 27 over the cube root of 432. So 432 will break down to, what was it? 216. So 2 and 216, 2 and 108, 2 and 54, 2 and 27, 9 and 3, 3 and 3. Okay, so the cube root of 27 is still just 3. But now the cube root of 432, there's a group of 2's, and there's a group of 3's, right? So 6 can come out, 2 times this 3. But then this 2 right here is going to stay underneath. Does that make sense? Okay. So now we don't like radicals in the bottom, right? We don't, and in the past, what we would do, because there's a square root, the square root's kind of a unique situation. It's the easier one when we do these. If it was a square root, we just multiply bottom by radical 2, top by radical 2, right? And that basically what we were doing is trying to force this to be a perfect square on the bottom. Okay, just trying to make a rational number. But now if I multiply by like even radical 2, that it won't even make right now sense to us. If I multiply by the cube root of 2, it's going to give me the cube root of 4 when I'm done, because I multiply inside by inside, right? Well, cube root of 4 is not a perfect cube. So I don't only want to multiply by a cube root of 4. What I want to do here is multiply by another cube root of 2. Because what's 2 times 2 times 2? 8. If I got the cube root of 8, or I could look at it this way, it'd be the cube root of 2 cubed, right? Those cancel out, leaving me just 2 on the bottom. Does that make sense, everybody? Okay. I've already got the 6 on the bottom from right there. And on the top, I would multiply by cube root of 2 times cube root of 2. So the top becomes 3 cube root of 4. We can cancel the 3 and the 12 on the bottom, so it'll be 1/4. So we can rewrite this as cube root of 4 over 4. Like I said, I'm not going to do that. We're not going to work on that right now, if at all. But people always get stuck and say, well, I've learned a pattern with square roots. I just multiply by what the radical is on the bottom. But you have to understand why we do that. The reason we're doing that is we're trying to make a perfect square on the bottom. Okay? So in this situation, I don't multiply by just the cube root. I'm going to multiply by cube root of 2 times cube root of 2 because I want to make a perfect cube on the bottom. Okay? Basically, this number, this index, will tell me how many total radicals I need to multiply by on the bottom. So if that was a 4 right there, that index was a 4, I would need to multiply by 4 through 2, 4 through 2, 4 through 2. I have 4 total. Now it's a situation in mathematics where just learning what we've done previously and being able to mimic or be robotic or just be a calculator to redo that hurts you here because we make the transition that it's the same thing, but it's mathematically or logically the same thing. It's not procedurally the same thing. Okay? So just make sure that we kind of grasp that. You got an assignment in Math Excel. 10 questions, due Friday. They're simpler, obviously. I think this is probably the hardest one you'll see. Okay, like a fraction and the cube root. Most of them are cube root. There's a couple in there that might be like 5th root, 7th root, but those are strictly like algebraic. The idea with like numbers, if I want to take the 7th root of a number and find a perfect 7th power for a value, those numbers got to be pretty big. Does that make sense? So your perfect cubes are obviously much larger numbers than your perfect squares. I don't even know what your perfect fourths and perfect fifths, I don't even know what you would call those. They're much bigger numbers as well. So usually what I'm trying to say is usually they don't deal with like the seventh root of a number. It's usually then all algebraic when we get to those larger indices.